Good evening and welcome to Caltech. I'm Harry Atwater, Chair of the Division of Engineering and Applied Science, and I want to welcome everyone here in person and also our online audience for the Watson Lecture tonight. The Division of Engineering and Applied Science is advancing science for the benefit of and to develop the technologies of the future across 7 diverse departments, including the Aerospace department, which is the home department for our speaker tonight, and many others, environmental science and engineering, medical engineering, computer science, so it's a very diverse group, but we're bound together by that common mission. And it's also notable in this year that this is the centennial of the Watson Lectures. For 100 years, Caltech faculty have been offering lectures that develop an appreciation for science, technology, engineering, and mathematics, and convey this to the public in simple and elegant arguments and terms. We're also supported here in this enterprise by the Friends of Beckman, and the Friends of Beckman supports the lecture series, and through their efforts, we have tonight students from Francisco Bravo Magnet School joining us. I want to say a little bit about Mory Gharib, our speaker tonight. He's going to tell us about an affair of the heart, an enigma of the heart, that is. But before that, I wanted to just tell you a little bit about Mory. I'm not going to say a lot because you're going to see a video that will give you an up-close and personal description. But I know Mory. He's been my colleague now for more than 30 years here at Caltech. He is the chair of our Aerospace department. He's the Hans Liepmann Professor of Aerospace Engineering. And he's the winner of many awards and accolades. He's been an entrepreneur who's translated inventions in his lab into industry. He's also most notably a member of the National Academy of Engineering and the National Academy of Inventors. But I think what really sort of sums up Mory to me is something I can tell you about a recent thing. Mory is among, in my travels, one of the most astute observers of nature and of human nature also at the same time. And one recent example of this is the work by his group looking through the manuscripts and drawings and documents of Leonardo da Vinci. I've been a longtime Leonardo geek, as many scientists and technologists are. But as you begin looking at the works of Leonardo, they are astounding in the level of inventiveness. And you would have thought that almost everything that could be known about Leonardo had already been found. But Mory's team, working together with him, was able to find, looking through the manuscripts of Leonardo, and Mory, of course, is a person that's concerned with how fluids move over materials. He's interested in fluids for autonomous flight of vehicles, fluids for that flow through the heart and through other medical devices that we add in the body. But in his work, he was able to see that Leonardo had developed ideas about laws of gravitation that were never actually clearly articulated and credited to him. We think of Newton as being the inventor of our laws of gravitation. But he found these ideas hidden in the manuscripts of Leonardo, and it really takes a trained eye to do that. And so I think that's a really telling example of the kinds of things that Mory brings to the world of science and engineering. So I'll let you see now a little bit more about Mory through his own words.
So I grew up in Tehran, Iran, and I had a fantastic teacher that really made me interested in going to physics. After coming to US, I got really interested in aeronautics and aerospace. Of course, the only place that you want to go is Caltech. So I applied and fortunately got accepted to work with one of the most amazing advisors, it's Anatol Rashko at Caltech. Well, the best thing is when you see a drone crashes. Yeah, it is funny. But I think we learned from our failures more than our successes. Because all the problems basically hide behind success, correct? You don't see them. But when you fail, you go back and look at them and you find out what was wrong. Hi, I'm Mory Gharib. I'm a faculty at Caltech, chair of Aerospace department and also director of Center for Autonomous Systems and Technologies at Caltech. When I was an assistant professor at University of California, San Diego, one of our colleagues at the University Hospital showed up in my lab. He bluntly asked me, are you an aeronautical engineer? I said, of course I am. So you know how to design, the airfoils and flaps and all those things. And I said, yes, of course. And I didn't expect him to come to the next question. Then he showed me a mechanical heart valve and said, can you guys design something better than this? And that's how it started. And I started to look at the heart of zebrafish because they are transparent in the first 4 days of their lives. And they show how heart is formed and worked and also how cardiovascular system evolved. I worked on projects that detect bubbles under the Navy ships. That was really basic science of how bubbles are formed, how it can be detected. And the funny part is that same microbubbles show up in heart valves. The same way we want to get rid of bubbles in wake of the ships, not to be detected by enemy radars. We're trying to get rid of bubbles in mechanical heart valves so they don't get to the brain. Almost the same physics. My favorite is when you do the discovery. That's the aha moment that I always encourage my students to search for. All the anomalies. I say respect the anomalies because maybe they are the one that contain the answer. That's my favorite discovery.
Thank you very much, and thank you, Harry, for your generous introduction. As you see from the title of my talk, tonight we're going to talk all about hearts. So please bear with me. It's going to be an interesting journey. I have to mention that even in the prehistoric time, heart has been always identified as one of the most important organs among all the organs of the animals. And even Egyptians thought that heart actually contains all the data or information about the good deeds and bad deeds of the deceased. That's why they weighed it, and basically they put the value on the person based on weight of the heart. And in Aztecs, sacrificial ceremonies, heart was the first organ that was taken out, because they wanted to separate the soul from the heart, from the body. And of course, in all of our religions, heart has been a symbol of love and giving. And Leonardo da Vinci used heart as perhaps we look at all the drawings and sketches he has made, heart has been always there as a prime example of how to represent nature. Then, the modern times, the sort of modern times, you have famous painters like Miro that in this painting, describes heart as he saw that. And and also the famous painting of the Kahlo, two Fridas. And you can see the hearts are kind of connected together through tubes. And then a third grader and Mrs. Martilla's, the art class also, draws something like that which is interesting. But my favorite is the one by Nadia Rosenthal, a good friend who is a physiologist at the Jackson Research Center. And she took a Persian F-shell rock pattern and put the DNA as a margin and the development of the heart through the 9 months as diagonal and vertical. And one of these days I'm going to order one of these, but it takes time. Now, but beyond its metaphorical significance, the heart is also an enigma that has fascinated philosophers, physicists, and scientists for centuries. But my talk today would be more from the perspective of an engineer, and more specifically from a Caltech one. And I have to confess that my original title was this. But then I realized if I put it there, maybe half of it won't show up. So, we decided to stick by the simpler one. At its most basic level, a heart is a muscular organ that pumps blood throughout the body and delivering oxygen and nutrients to the cells, removing waste products, and also its structure is remarkably intricate with 4 chambers, with 4 chambers, left ventricle and right ventricles, and 4 valves. It's a fascinating physiological machine. If you look at the range of pressures that heart works from almost 0 to 120 minutes of mercury and beats up to 2 billion times over our lifetime, we can't find any mechanical machine that lasts that long. Of course, we have to take care of our hearts to do that performance. And it's also, one should notice that the heart pump, as we call it, actually consists of 2 pumps in series. And left ventricle is the one that carries most of the load. Now, the heart is more than just a pump. It's also a sensory organ that can detect changes in environment and respond to them in a complex ways. It has many sensors, neuroreceptors, or we call it baroreceptors. They're sensitive to pressure, and some sensors in the aorta, and directly send that information to part of the brain that is not in the decision making, but is basically coordinates the information. And after the information is received and coordination by medulla is sent back to heart, and then the heart, based on instruction that receives, responds to it. Have you noticed that you cannot control your heart rate, or you cannot control your blood pressure? Why? Because we are having with one of the most impressive autonomous systems in nature. It's completely independent, and as long as it's taken care of, it's better than any other autonomous system that you are driving around. The next step, I would like to give you some interesting information about the heart. And I start with the concept of, in some aspects of it, size does not matter. And what are those? Well, think of a shrew, North American shrew. It hearts only weighs 2 grams, and it beats at 850 beats per minute. Now, if look at the human heart, it's about 300 grams and beats about 70 beats per minute. And the blue whale is about 100,000 grams and beats at 20 beats per minute. Now, what is common among this that does not depend on the size is that each of these hearts pumps about 200 million liters of blood per kilograms of body weight. So it doesn't matter if you're a shrew or a human or blue whale, this number is almost constant because we are all mammalians made out of same type of cells. And then before our heart's working life is over, each heart delivers about 38 liters of oxygen per grams of our tissues. And liter is basically a gallon is about 4 liters. Now, the most impressive one is when you think about it, our heart beats about 100,000 times a day, and it can fill an Olympic swimming pool every year. And that's very impressive. And you ask yourself, from engineering point of view, how does it do it? So to answer that question, we start with the parameters that we call ejection fraction. So every time our heart beats, the left ventricle pumps out certain amount of blood that we call a stroke volume. And if you divide that cube by the volume of the left ventricle in diastole when it's relaxed, the ratio is ejection fraction. On the average for healthy human beings, we are about ejection fraction of 64% considered healthy. And then you can see that the cardiac output, which is what your body needs to see in order to function either at rest or you're running, it goes with heart rate should be multiplied by the stroke volume, which is the amount of this little cube here. And it's important to keep it up to 64%. Now, the Enigma starts with the following observations. If you look at these cells up here, you will see that these are cardiomyocytes. These are cells that our heart are built from. And it only contracts 15% of its length. It's about this much, only 15% shortening and extending back. Now, if you look at the dynamics of the heart itself, you see it's really impressive. This is a heart that is open heart surgery. And you see that, expecting, such a motion from just 15% contraction, every engineer is going to ask how, because I want to build one. So this is Enigma part 1, which we ask in the cardiomyocytes, that muscle cells can only contract to 15% of the total length that they have. So how can they produce such a 64% squeezing efficiency? Well, let's do this at a little geometrical game here. Suppose I give you a cylinder and say, okay, put these muscle cells anywhere you want. So we start with something simple. Let's say this is the cylinder I gave you, and I say I want to get 64%. So you start to put it linearly like this, which you only can contract 15%, and then ejection fraction is going to be only the 15% too. But if I put it like a circumferential, then the ejection fraction only can be 30%. So now you can see that the simple approaches would not give you that 64% that you see in your heart. But nature gives us some clues. And those clues include something that may help us to answer this question. Is that if you look at the natural designs, from the squid mantle to pneumatids, the ratio that you get with the fiber angles is that if you put it in a helical pattern, can give you ejection fractions that you want. So nature says, forget about linear, forget about the simple circumference approach, just put it in a helical band. And it's possible to get that 65% ejection fraction if you find the right angle. Now, what this has to do with our heart? In 1969, there was a very important discovery by Streeter, who was a cardiologist. What he did was that he took a heart and did a cross-section and looked at the wall of the heart. What he realized that was from the epicardium to endocardium. These are fancy names for epicardium means basically the inside, and endocardium is inside, and epicardium is outside of the wall. And he realized that the muscle or the muscle tissues, they change the direction as they go from inside to outside the wall. So this is plotted here. So what does it mean? It means that you have a wall of the heart, imagine this, that the bands or the fiber tissues actually are like this. Okay? They are not all going in the same direction through the thickness of the wall. And then in 2005, with advances of the MRI technique, the papers showed up in this beautiful picture of using the technique of diffusion tensor MRI that actually can tell you the direction of the muscles, not the dynamics of it, just how they're patterned around the heart. And you see that actually the bands are outside in this direction and inside in the red one, a different direction. And somehow they're connected. It wasn't clear how. That MRI image prompted a very famous thoracic surgeon, Francis Torrent-Wasp in Spain, to say, okay, if that's true, how come nobody has seen this? So he came up with a very interesting idea. He took a calf heart, something like this in my hand, and he said, okay, if these bands are existing, at the boundaries, a collagen, and maybe I can remove the collagens. So he actually boiled the heart and for 20 minutes, and then he took the heart out and actually did not use any knife, put his hand and opened it up, like the image that you see over there. And this is this one. For some of you can't see, I'm going to do it right here. Okay? And this is actual, but 3D image of the same calf heart that he actually did that experiment. And this was a huge revelation because for the first time we see that nature is not as boring as we thought. You know, just put a piece of meat and just send a signal and just contracts and then let go. So it was actually a more interesting design behind the whole concept of this. Now, this discovery now prompted some of us at Caltech. Actually, Pakotron's was actually in our lab, and as a sabbatical, I spent about 6 months work with my students, and we did something, a series of systematic studies of finding what is the impact of this helical double bands, and then how does it really work? What is the dynamics? So we started with looking at different aspects of it. Like, we know that from physiology, that when the brain sends a signal to the heart, they go to 2 little pacemakers here that they sit right on top of the right heart. And what happens is that they basically control the signal transmission through Purkinje, they call it Purkinje system here, that goes through the septum of the heart, goes to the apex. So what happens is that the apex, the first signal arrives, and then heart starts to see the signals that contract. Previously, everybody thought that the signal from here just propagates uniformly through the heart and makes the contraction. But when we did the MRI technique that actually can identify or trace how the contraction actually travels, we found that actually it starts at the apex, that was well known, but the way it went actually it was something like this. It follows the same band. Actually, the contraction, according to MRI studies, shows that actually the contraction starts here and went through this and came back and went up. Well, that was interesting. But what is more interesting was that when we look at the cycle, the time that this contraction happens was covering both systolic and diastolic phase. What does it mean? It means the whole contraction and expansion are due to contraction of this band. And we know contraction is usually correlated with, squeezing. But this model actually shows that it's possible that one contraction, depending on its phase and how it travels through this magical band, can squeeze and dynamically open it up. Before, everybody thought that you could squeeze and then you relax. And that's only a sick heart that does that, according to some of the studies that was done later on. But it wasn't actually clear to us. We decided to do some experimental model, computational modeling, I'm sorry. So what we did, basically, we followed exactly the same band, and we sent a contraction through apex to this double helix. As you can see over here, this band, the apex is almost fixed, and the top of the base of the heart comes down, and you can see that as it goes through diastole, it increases the volume, and it goes through same contraction band. It can squeeze it to that 64% that we need to have. This was done by Anja Grossberg in my lab, and later on we built a physical model that not only showed the traveling of this contracting the contracting, the signal, but also showed that it can produce the same torsion that we see in this live heart. So a healthy heart actually starts with a systole and goes like this, torsion, and a sick heart does not show that torsion. What does it mean? It means that a healthy heart goes like this, and a sick heart goes like this. And this has been observed in the disease called cardiomyopathy. When the heart expands so much, it cannot really do any more torsion. It just opens up and closes. And ejection fraction as a result of that, as we showed, goes down to 40%. If it goes down to 30%, then that person needs to have a heart transplant, basically. So now this is the model that we built, and also depicts the torsional aspect of this, which intimately related to the way that this helical fiber band is wrapped around the cavity of the whole heart. Now, and we showed that, by using this new concept from Torrent Guasp and the work that has been done in Caltech, that you can explain why you can have the 64% ejection fraction for the healthy heart. Well, this was the first Enigma, and it took us many years, but we think now we have answers, and now it's showing up in all modern physiology books as they explained the operation of the heart. Now, the Enigma part 2 is that why does my cardiologist tell me to keep our heartbeat, or my heartbeat, between 60 and 90 beat per minute? BPM means beat per minute. And I really encourage you next time, ask your doctor and cardiologist, because we can explain that based on things that your body needs to have the cardiac output. So your 60 or 90 depends on how much your body needs in terms of metabolic demands it has in order for blood to deliver the oxygen. But has not been ever quantitatively shown. And also, it was not really something the engineers like to accept. They always try to find a more explicit or exact reason why this heartbeat range is chosen. So to do that, we let's go back to first a slide that I ask you to disregard everything I spoke about in the first half of my talk, convincing you that the size does not matter, because now I'm going to convince you that size matters depending on what you're looking after. So let's go back to our size slide, and here again, I would like to draw your attention to this heartbeats for different sizes, and human to blue whale. Now, what we can do is that think of, let's put all the animals that we can measure their heartbeat and their life expectancy, and see how does it work. So if you look at pygmy, again, it beats about 1 billion beats, and that the 2 beats per minute, and it's also, I'm sorry, at 800 to read it right. And lives 2 years. And the mouse is about 1.31 billion, 500 beats per minute, 5 years. Cat and horse, and all of them except human, they're around 1 billion beats. So that's interesting, okay? And it seems that all of us are assigned a certain number of beats to live on. And then you may ask, what happens to human and giraffes? Personally, frankly, I don't know what giraffe does to live longer, but I know that we have good doctors that helping us to live few years longer, okay? And also look at their lifestyle. This actually in 15th centuries, the average life, the span of a human being was about 35 to 40 years. So we have really improved, and basically we deviated from the evolutionary, the trend in this respect. Now, this the heartbeat theory is it's really qualitative, And we need to really look at other aspects to explain or answer the Enigma 2. So what is the secret of choosing the right heart rate, or heartbeat? And why does the mammalian heart care about the heart rate? Now, to answer this question, we need to first find out, how did we end up with such a superb machine? All of us, mammalians and vertebrates, our heart starts with a simple tube that, pumps, and our first heart contraction commences. Our vertebrate heart has a shape of a tube. All of us, mammalians. Now, if you look at the development of the heart within 9 months, from the tube, this is for human, to when the tube basically starts with, the turning and making the cavities, and eventually formed into a 4-chamber cavity here. We go through this process. And the interesting thing is that if we look at this development is actually at every stage is very similar to final design of certain other, the vertebrates, like fish, for sea looping. Then we look like a frog, our heart, I mean, and then the reptile, and then to alligators. Well, it's interesting because these are all in the final stages, but in 9 months we go about millions of years. And this is, again, the concept of natural design and convergence in design. But every animal, depending on where an environment they end up, they have enough for sustaining their lives, and then the process of design stops, or evolution stops. Now, for me as an engineer, I really like to go back to the tube and find out how this really formed. We have only 300 cells. How do they arrange themselves? How do they mechanically form into final chambered house, the heart? Now, nice thing is that nature also offers the solution, because I cannot go for any mammalian, the cows or cats or dogs, try to see the first 20 hours how the cells came together. It's impossible because it's not visible. It's also by the time you get there invasively, you distort everything. So zebrafish is the answer. Why? Because zebrafish, in its embryonic stages, it's so small. Actually, it's over there compared to penny. But what is amazing about this machine is that it's transparent. That means that you can look through it. So up to 5 days, all the zebrafish is actually transparent. You can see through them. And one of the things we were after was this little heart. So what if we can go even to 1 day and it starts to watch it continuously? So I was very lucky here when I started to look at this. I worked with Professor Scott Fraser, my former colleague, and he generously took me to his lab and showed me this video, and that was based on a device that he actually invented, fast confocal microscopy. And this is interesting. So Vic at that time kept this embryonic zebrafish in agars, which is like a gel, and so it won't move around. And then under microscope, we image it. And you can see that this is a 2-chamber heart and provides circulation around the eye and the rest of the body. Well, for me, this was heaven, because now I can say, okay, Scott, can you go back maybe 20 hours, right, and 4 days? And he, with his team, actually provided that. But before that, just to show the difficulty of imaging, this whole heart that you see here fits into human hair. What does it mean? That you have such a dynamic thing within the small, the confinement or real estate, which is by itself is amazing, fascinating natural design. Now, this is actually the confocal microscopy that maps this is the atrium, pushes the blood into ventricle, and then these little things are heart valves. They are only 5 micron. And then this is the bulbous that every time it shoots the flow through it, it then goes to the rest of the body. Well, for us, that was even too late. We wanted to go way back. So in this case, you see the tube that starts at different stages. That's 34 hours post-fertilization, 36 hours post-fertilization. And eventually, forms the two chambers. And you can see that that video is a little bit delayed compared to this. Now this is that stage. You can see the two chambers and bits. Remember that this nature needs to provide blood current into the rest of the body. So it's different than the factories like in like a Ford assembly line. You order all the parts, but you only assemble it at the end, and you turn on the engine. This one, imagine that the car should be there and just deform or form into new shapes, and through the whole process has to be active and provide the vital circulation that body needs in order to survive. Okay, so it's a quite different manufacturing or fabrication process than what we have in our industry. So now the question was, in early stages, there is no valve. Remember that in order to get the positive displacement, you push, flow goes in one direction. It cannot come back because you have a valve. It can only go in one direction. This machine, the tube, does not have any valve, but it still can pump. So now you can imagine that you have different theories that how this machine works. One theory is that it's peristaltic. That means you squeeze it and move it, and that way blood moves. If that was true, then you get this dashed line. That means with the heart rate increasing and the average velocity, which is basically cardiac output, it should stay in this straight line because you're only changing the frequency. Stroke volume is the same. But when we did the observation through measurements, actually the blood cells through the heart, we realized that actually it's not linear. It has resonance frequency. It has some frequencies that it prefers over other ones because it perhaps reduces the amount of energy that cells need in order to move the flow. Well, some of you may ask, how did you change the heart rate of the zebrafish? So the little trick that Scott showed me was that once the fish is in the agarose, not frozen, but not moving, they add little coffee. And with different amount of little drops of coffee, you can increase the heart rate. So there are different tricks that biologists know that engineers never touch. So in that respect, there are lots of learning be done. Now, we asked, okay, so if it's not peristaltic, what kind of pumping, what mechanism is there? So when we studied every cell, remember these are only 300 cells, and we realized that only cells in this area that are active. That means they contract simultaneously. The rest of the cells actually like the passive tubes, like something like this. If you look at here, and you see that, imagine that you have the cell, the black lines are acting, mimicking the cells, and the rest of the tube is not active. And later on, we confirmed that by looking at the calcium actually release. So yes, those cells, they're just following. They're a slave. They are not master. Quite different than the peristaltic. And that was interesting because we thought that we discovered something new. And running back to the lab, we said, OK, if it's true, let's take the elastic tube and use our toothbrush vibrator and just pinch it, touch it like this. And amazingly, we saw that actually this particle is moving very fast. And if we change the location going there, you can see that flow that precisely mimicked what we saw in the embryonic heart of the zebrafish. It has resonance peaks. Change the location, flow went backward. So by changing the location, if you put symmetrically, nothing happens. It's straight, no flow. So this was a great discovery until we found that actually this was discovered in 1954 by a German thoracic surgeon named Liepmann. And also we found that if we change the frequency, we can reverse the flow. So we can stay in one point and just sweep the frequency, and you see that you have positive flow in one direction, and then suddenly it goes negative, which is fantastic for engineers because now we can design pumps that we can control the direction of the flow just by changing the frequency. And this is an artist, the rendering of the mechanism of Liebau, that you have the pinchers as cells, and they, based on right frequency, can create a resonance and creates low pressure here and sucks the fluid in one direction. And this was confirmed by doing ultrasound imaging on the same tube. Well, okay, now we look at this. We say, okay, you have a tube, 300 cells, cleverly designed by nature, 300, a few cells here, contract, send a wave, and the right frequency, they have the right flow. Right frequency, right flow. It's very important because it's only certain heart rates that can provide that optimality. So it's the beginning of the story. Now, what happens when we go from the tubal stage to full heart? Then what happens to these cells? They become actually this sinoventricle cells that, the pacemakers of the right heart. But going back, so we propose that, this heart now, that it forms into tubular heart, forms into actual heart. Some of the leftovers of the tubes that deliver the blood still hang around, and that's our aorta. Okay? And studies have shown that they have actually the very compliant nature and have even some muscles in them. So the question here is that the proposal is that we go from tubular with the pinching cells into a tubular pump, but now the pincher is our heart. What does it mean? That every time heart beats, sends a pressure wave, and how does this compliant tube, which is our aorta, reflect or respond to it is a very important part of the story that I'm going to tell next. So first thing is that the old view was that we have, apologies for this, that we have the heart as the pump, and the rest of the system is just the piping. No impact on the pumping efficiency of the heart or the system. New view, based on what I'm going to explain, is going to say that we have a system that has subsystem. One of them is heart, that is a positive displacement, and the aorta can be also acting like a passive pump, excited by the heart. So here, this is the new view of how we look at the cardiovascular pump. So it's not just the heart, but the heart and the aorta together. Well, the good news is that if the aorta collaborates with you, works with you, your pump is going to feel happy because it says that they are pumping something, my aorta also helping it by giving it extra push. Well, that's good, but remember that I showed if the heart rate changes, actually you may have flow that is going to go backward. Okay, so that gives you the clue where I'm going, correct? So you need to have a matching between the heart and the heart pumping rate and the aorta that allows you to stay in this way, in this side of the curve than the other side. So you don't want your aorta to work against you. Well, let's study that. So this was part of the thesis of Nemo Palavan, who's now a professor at USC. And he showed through his elegant in vitro experiments that if you take an in vitro experiment, means that we model certain type of human cardiovascular system. So in this case, perhaps is a 45 years old, based on elasticity that we give to the aorta and the heart and everything else. It's a complicated machine, but it tells you something very interesting. As you change the heart rate, you can see that the flow, it can go from this phase, which is helping you, to this phase, which is not helping you. And then if you can go higher, you may come back and help you again. But it's very hard to sustain the 180 beats per minute in a resting condition, okay? So this was a big discovery because it now allows me to tell, yes, the optimal condition for choosing the heart rate is the one that actually makes you to always have the help from the aorta in order to heart to spend less energy. You can think about this. This poor machine should beat for 2 billion times. And even the little help is going to help you or help the machine to sustain its longevity. So in that respect, I think we have a more engineering answer to Enigma Part 2. Now, of course, different people, different sizes, they will have this curve go back and forth. So maybe 90 bits per minute is good for certain people, it's not for other people. But now with computer modeling, we should be able, to measure the elasticity of aorta and the heart and give a range which is more fitable to your kind of body structure. And that is a very promising, the avenue for finding it, what is the proper the heart rate for your condition. Now, the last enigma that I'm going to talk about is the enigma of number 3. And the question is, does the heart's pulse encode information about our health? Well, up to now, everything was about the rate. But now we are talking about the pressure wave that we send through the whole body. Can that one contain information that we can use it to do diagnostics? To start with, we should understand that as we showed in this animation, every time perhaps the first bits of your heartbeat, it has a shape like this. After that, as the waves go back and forth, they reflect from any divergence, any branch, anything that is underway, and they send a signal back, reflection. And that brings the information back. It's exactly like radar. In radar, we send a radio wave, it hits an airplane and comes back. We compare what we send in with the one that comes back, and we say, okay, now there's something over there. And that's the whole idea. We want to see if there are encoded information here that we can extract and to be able to get this vital information for diagnosis or for other strategies for treatment. Well, this is nothing new. We know that from Chinese medicine, there are ways of qualitative can take you what stages of disease you have or what kind of disease you have. Well, and also that this all documented in Canons of Avicenna. In this one, he tries to tell if from the signal from the waist that if the princess is in love or not. So there's a whole chapter on reading the right pulse for finding that effect. So, but for us, we try to do a digital version of it. And our approach has been, look, we learned about the impedance pump, the resonance pump. So the aorta by itself is important to be studied. And when the aortic valve opens, heart and aorta are connected. Now, this connection is the total system. Now, when the aortic valve closes, there's no communication between the heart and the rest of the aorta, so it becomes a completely different system. Now, if you look at the pulse pressure wave, this is taken from, say, aorta, you will see that in this case, this part of the wave is representing something that the whole, the complete system, heart and aorta together. But after this line to the right, it only represents wave conditions in the aorta. So it's more vascular part of the body, the cardiovascular systems, than the heart itself. And then what we did, which thanks to Professor Howe and his group, they came up at Caltech, they came up with a very fancy way of, say, some of you know what Fourier transform is to look at the signal within a unknown signal. So component signals within that. So imagine that if I look at this part, this shape is because all the reflections that went back and forth and formed this shape. Now, this part of it is all the waves that went back and forth between the aortic valve and the rest of the cardiovascular system. Now, how do you decipher this? Like, read the code. What kind of code is embedded in this? And that his technique allowed us to do it. I'm not going to go through mathematics, but what we did is that we looked at this, and by looking using Howe's technique, we were able to come up with one index. We call it omega 1. And this omega 1 is not constant within that. It fluctuates like this, but you can actually optimize it and on the average get one number. And you can do the same thing for the right side, which is only aorta, and you get another number. So we call it omega 1, omega 2. Very good, because now if you give me your pulse pressures, I can say your omega 1 is this, your omega 2 is that. But what does it mean, really? And that's what the Pahlavan and Dr. Ray Matthews at USC is the head of the interventional cardiology. And they found out that something interesting. This is based on published data. It says that, if you calculate omega 1, remember, that is mainly dominated by the heart, but there's a total system, that you like to stay below this number, 110. And this is not the heart rate. Please don't get confused. The only reason it has beats per minute because it has the units of 1/time. So the idea is that all the healthy people are here, and diseased people, the diseased heart actually give numbers above that. So for heart failure, we are here, and for rest of us, healthy ones down here. Well, that was really interesting for us to discover. And then what happens to omega 2? Omega 2 tells me that actually it changes with age, which is true because our vascular system, just vascular, remember this is the aorta part, ages and also the more influenced by the environment that we operate or we live on. If you smoke, for example, your aorta gets more stiffer, waves travel faster, and influences the omega 2. Now, in this case, you can see that naturally omega 2 drops, but for vascular diseases, there's a number here that they identified that is below that line. So you can suddenly we saw the power of this intrinsic frequency, we called it omega 1, omega 2, in hopefully predicting conditions for vascular diseases and conditions for the heart itself. Now, then something very interesting happened. We said, okay, what's the difference of these two numbers, omega 1 and omega 2? Let's subtract from each other. And then see what happens under different conditions that we may have. As you know, as we age, as the pulse pressure wave goes through the vascular system, it has different shapes. Now, when we plotted the difference between those two numbers versus age, we get this line, and we see that all the diseased cases are above this line. And that was interesting. But what was more interesting was that if I'm 50 years old, I'm healthy, the difference between those two numbers is also 50. So it seems that the difference is actually your cardiovascular age. It corresponds with that one, which is also very interesting because you can imagine that, if you are 60, you're supposed to be here, but if you're here, your cardiovascular age might be 75 or 70. And so it seems that the disease stages or states influence this cardiovascular age, and it's a parameters that's under study, and we're trying to see how we can incorporate it in other diagnostics that we can provide. Now, through the last slides, this if you show this set of indices to your cardiologist, they said, it's really fantastic if you give me all of this. I can really start to work on if you have any problems you have. Okay, your ejection fraction and your pulse wave velocity, which is stiffness of the vessels, and other parameters. But this parameter pops out as holy grail of all the indices for cardiovascular disease, which is mainly heart failure. So going back to intrinsic frequency, major studies done on 4,500 people called Framingham studies. And this study shows that intrinsic frequency can be used as an important index to predict the heart failure. And this is over large studies over 25 years that has been done, that the pulse pressure wave was available, and we conducted these studies with the NIH group. Now, the question here is that can we connect these directly or more explicitly to LVDP? And what is LVDP? LVDP is the pressure right here, down here. Imagine that, when your heart relaxes in the end of diastolic, it has to now build up tension in order to open up the aortic valve and push the blood out. The level of that pressure is very important. If it's low, it's good. If you have to build up lots of pressure in order to open up the valve, it's not a good sign. That means something wrong with the afterload, after resistance that you're going to see. So in general, we like to keep that LVDP below 10. 5 is very good. But when you get to numbers like 15 or 18, you should better see your doctor. So how do we measure that if it's that important? Why don't we do it every day? Well, the problem is that you need to really do it invasively. That means to measure that pressure, I need to send a catheter into your left heart and measure it, physically to measure it. And this is not something pleasant that you want to do every 6 months. And also the other approaches where they use sensors implanted, they're very risky. So the idea was, can we use this omega-1, omega-2 concept to actually predict the LVDP non-invasively? And that's, again, the work that's done by Dr. Pahlavan and my group and Alicia Tamburini, graduate student that's sitting in front. And they came up with some interesting approaches. Tamburini actually took a cough pressure they can buy from CVS and modified it to be so sensitive to faithfully, basically trace the pulse pressure waves from the cough. And then they used that in large studies that done at 5 centers, and they tried to correlate and find out what's the relationship between high fidelity aortic signal, the cough signal, with the actual pressure in the heart. And through some complicated AI machine learning in this case, they were able to find that nice correlation, the coefficient factor of about 84, which is pretty on par with every other medical modalities that you find today, if FDA wants to look at it. So suddenly, you can imagine that in the future of cardiology, we think of a system that, with a cough, and if you want ECG, and then get the signals, and then use AI and machine learning to get all the elements that you need to have to provide it to your cardiologist in real time, so they can either monitor you or tell you what you need to do in order to avoid or have a healthier lifestyle. With this, I would like to just summarize the enigmas that I addressed. They are not the only enigmas. I'm sure there are more questions, but these are the ones from engineering point of view were actually interesting to us, and we did our best to answer those. Now, with this, I would like to put my disclaimer. I'm not a physician, I'm not a doctor, and in this cartoon, which is real, showed up in LA Times many years ago, somebody had a heart attack in a movie theater, and people say, "There's a doctor here." And this guy say, "Okay, I have an aeronautics degree from Caltech." So with this, I would like to stop and thank all the collaborators over many years, and the group of visitors, and also recently the group that really helped me to put together this talk. And with this, thank you, and we are open for questions.
Hi, Professor Gharib. This question is from Lori online. Do your findings about how a normal heart actively releases/expands present any new ideas on how to treat cardiomyopathy?
Well, I think there are other biomarkers that can identify cardiomyopathy besides the regular imagings like MRI. And so again, I'm not a doctor, so I cannot answer that. Thank you. Yes.
Thank you for the amazing lecture, Mory. It's amazing to see that, in the development of human heart over 9 months period, they replace the natural evolution over several billion years. So my question is, because we are still in the trend of natural evolution, do you, from an engineer perspective, see any future improvement for heart development? Can we do better? Is there room for the heart improvement? Is my question.
Well, it's an interesting question, but a tough question. Okay, it's from our point of view, yes. The future is going to depend on the combination of better diagnostics and also bringing machine learning and AI into this. There was a very interesting article today about this in Wall Street Journal. I think the point is that to bring these advances into the masses, that means democratize the medicine, okay, by pushing the science of the diagnostics, the sensors that can be easily produced and put in those machines. And I think in that respect, the future is open to all of this. That's all. Thank you.
One more question, Professor Gharib. What is the next avenue or the next enigma that you're looking at of the heart?
Well, as I mentioned, there are many few, actually I kind of refrained myself to put the fourth enigma, but now you ask, I will put it in. So, from Leonardo da Vinci to modern physiology experts, if I ask why nature picked up 4 different valve designs in the same heart, I don't know the answer. And I don't think that, so I challenge us, all the students, graduate students, that this is a good, well, I go back, this is a very good, difficult one. I think I started with the easy ones. So I leave the difficult ones for the rest of you. So that's interesting, the mitral valve is a bileaflet. Aortic valve is a trileaflet. When you go to pulmonary, they become cusp, right, and just simple design of the curved shape. Why? I don't know. If you look at the all animal kingdom, any animal that has these valves, if they have the right heart, completely different design. Within the ventricle side, it seems only humans have this deviation from trileaflet to bileaflet. Again, it's very interesting engineering question. I can come up with a 5th one, but I think it's getting there. Thank you very much again. You have a question? Oh.